So good morning. Right. So we'll be discussing the sources and sinks. So the next topic will be the method of images. So in the method of images, right? Suppose if there is a boundary that is present, so maybe a rigid boundary, right? So suppose if I have a rigid boundary here, and this is the fluid, and then in this fluid, on the other side, there is no fluid, let us say. Now, to simulate this kind of scenario, what we will do is, suppose if there is a source that got placed here, and for this source, it will continuously generate the fluid in all the directions. So in all the directions, the fluid is flowing. Now, if you notice here exactly, this boundary will make the fluid to flow in a tangential direction like this, right? So to assure this kind of scenario for the analysis purpose, what we will do is there has to be an image on the other side so that my flow of the fluid exactly on the boundary will be tangential to the surface. Got it? The arrangement of such kind of system we call as the method of image for the original system. Got it? So to make sure that the analysis is not disturbed, suppose if it is having a distance of minus a, then this will be at plus a. So equal source has to be placed so that the analysis will not go wrong. So this method we call as the method of images. So this system of arrangement is called as the system of arrangement of sources and sinks. For accurate model of the fluid flow. When there are sources and sinks present. Is called image system. Right. So suppose actually if there are some sources and sinks present, under such kind of scenario, if there is a boundary that got placed, so because of the presence of this boundary and the presence of the sources and sinks on one side, so for accurate analysis purpose on the boundary, you have to bring in some more sources and sinks so that our analysis will not go wrong on the boundary. Such system is called as the system of arrangements for the image system. That's what we call as the image system. So essential components in the image system are there has to be a rigid boundary and there has to be presence of some sources and sinks. Got it? Okay. So this is for a plane boundary. So this is a plane. And the next one is there is something called circle theorem. So what circle theorem says is, suppose if there is an infinite fluid like this, infinite fluid we mean there is a continuous fluid flow that is happening. Now this flow will happen because of some complex potential presence, right? So as there is a complex potential, the fluid will be moving from one place to another place. Let us say the complex potential is f of z. So W is equal to f of z. Be the complex potential at any point in the presence of the infinite fluid. Now, suppose if you introduce a rigid circle like this, rigid circle we mean we have introduced a cylinder from the top. So the cross sectional is nothing but the circle, right? So we have introduced the cylinder in this. Now, because of the presence of this cylinder, the fluid will not go like this, right? So this will not go like this. So it will take turns like this. Got it? And inside also if there is a fluid, right? So that will be like this. Now, the complex potential or the fluid flow, that will make sure the proper complex potential, right? So if there is a complex potential here f of z, then the complex potential here, it will be f bar of z bar. Now, at any instant, if you notice, the total complex potential will be f of z plus f bar of z bar. This is the complex potential after the introduction of cylinder, and this is what we call as the circle theorem. Not inside. So let us say if you take the complex potential at any point, earlier it was f of z. Now I have introduced the cylinder. Now at that place, the complex potential will become f of z plus f bar of z bar. Got it or not? F of z plus f bar of z bar. So these two sum together will give the total complex potential after introduction of the cylinder. And this is what we call as the circle theorem. Got it? So this circle theorem is useful for the analysis of the image system when there are presence of the sources and sinks in a cylinder. For example, if you take a cylinder like this, let us say this is the diameter. So from here to here, this is the diameter. I have introduced the source at this point of strength plus m. Now the image system of this will be exactly, so let us say this is at a distance of a, then this point will be 1 by a. This point will be 1 by a. So or else actually if this is at a location of f, then so this point, let us say this radius is a, this distance is f and the radius is a, and here the image point we call in case of circle as a square by f. A square by f, where a is the radius. Now here this is the actual source that got present. This is the image, but it will not assure the total complete flow along the circle should be tangential. That is, the fluid flow has to be tangential on this particular surface, right? So that's what is the boundary by definition. Now, if the fluid has to flow in this direction, because of the presence of this source, you have to introduce an image source here of magnitude same plus m, and there has to be a sink that should be present here of magnitude minus m. So one source, one sink, and the actual source. All these three together will form the image system, so that on the boundary of this particular cylinder, the fluid flow is tangential like this. Got it or not? And this will be derived with the help of this circle theorem. This circle theorem says that at any instant, the complex potential will be sum of f of z plus f bar of z bar after introduction of any cylinder. Clear? Understood or not? Is this understood? Okay. So this is just method of images. So this system of arrangement. So by definition, the system of arrangement of all the sources and sinks to assure accurate flow on the boundary is called image system. So that assurance, for two different cases we are going to analyze it. One case is when there is a rigid boundary of surface like this in a plane. Now in this case, if there is a source presence here, you have to introduce corresponding source on the other side, so that the fluid flow on the boundary is exactly tangential. So because when there is a rigid boundary, right, the fluid will not cross the boundary and go, right? So it has to stop here. That means if the fluid is coming till this point, it has to go tangentially at any point. So this system of arrangement of sources and sinks, which will assure the tangential flow, is called the image system. Now in case of circle, what happens is you have introduced a cylinder here. Now, this circle, it has to assure that the flow of the fluid on the circle, it has to be tangential. For that, you have to introduce the sources and sinks as the method of system, as a image system. That image system would contain one source outside, one source inside, exactly the counterpoint. This counterpoint will be a square by f. So this location is f and this location is a square by f, where a is the radius. And one sink, it has to be exactly at the center. Suppose if this is a sink, then one sink here and one source here. Got it? So this is what we call as the circle theorem. You can note down this. Yeah. So the problems that are going to be asked in case of method of images are, he will be asking us to find out the streamlines. So, but the problem is very, very simple. So this is, understanding the concept is a little bit tough, but rather than that, solving the problems is easier. Why? Because this is all for us only the complex potential. So when there is a presence of a source or sink, you have to model as a complex potential as minus m log z. And then you have to add all the complex potentials together and then separate the real part and imaginary part. Real part will give the scalar potential and the imaginary part will give the fluid flow direction or the streamlines. Got it? So for us it is simply a complex analysis. Note it down. Circle theorem will be used to find out the image system for a circle. Note down one problem. What arrangement of sources and sinks will give rise to the function W equal to f of z. Sorry, W equal to log of z minus a square by z draw a rough sketch of the streamlines to this curve and prove that two of them subdivide into the circle. Subdivide into the circle R equal to A and the axis of Y. So here actually, what arrangement of sources and sinks will give rise to the function W is equal to log of Z. Yeah. So W is equal to log of Z minus A square by Z. and draw a rough sketch of the streamlines to this curve and prove that two of them subdivide into the circle r is equal to a and the axis of y. Now two of them actually, here actually what he means is the sources and sink arrangement whatever is given by this particular complex potential arrangement, those two sources will be subdividing the circle r is equal to a and the axis of y. Got it? So here actually r is equal to a is a circle in polar form and axis of y is in Cartesian coordinate. So in fluid dynamics problems, mostly he will be mixing both the coordinate systems together. So most of the times actually that is the kind of cases actually you are going to notice it. Now here this is straightforward and simple. What he has given is the complex potential of the arrangement of the sources and sinks. Now we have to dig it back so that you can identify the presence of the sources and sinks based on this complex potential. See this, W is equal to log of Z minus A square by Z. Now this can be written as log of Z square minus A square divided by Z, and this is log of Z plus A into Z minus A divided by Z. So this can be written as log Z plus A plus log Z minus A minus log Z. See this, now actually this is like m log Z plus A, m log Z minus A and m log Z, where m is equal to 1. Now that means there is a so minus m log Z is the source and this is a sink and this is a sink. Understood? Because the complex potential of a source the complex potential of your source is nothing but m log Z minus. So minus m log Z is the complex potential of your source, and for your sink it is plus m log Z. This is the complex potential. Now if you notice, there is a sink that is present at Z is equal to minus A, there is a sink that is present at Z is equal to A, and there is a source that is present at Z is equal to 0. So the arrangement would contain, so this is the source, this is at Z is equal to A, this is a sink, and then exactly at Z is equal to minus A, there is one more sink. So this is the arrangement of the sources and sinks, which will give rise to the complex potential of f of Z is equal to log of Z minus A square by Z. So this is it at any instant Z. So you have randomly selected the location Z at this particular point because of the presence of the sources and sinks on this line. The complex potential here it will be, so f of Z. So this is the point Z and f of Z is equal to log of Z minus A square by Z. So where A is the distance from here to here. Got it? So this is the complex potential. Randomly, if you notice any point, this will be the complex potential. Now, this complex potential is essential for us to understand the flow direction at this particular point and to know the scalar potential at this particular point. That can be found by dividing this into the real and imaginary parts separately. So here, this is the complex potential we have divided into the sources and sinks. Now, from this arrangement, you can divide the real part and imaginary part by taking Z is equal to x plus Iy, and then the real part we call as the scalar potential and the imaginary part we call as the streamline function. So just we need to divide this into the real and imaginary parts. That is the only task that is left over. And this question was asked in UPSC long time back. Got it? I don't remember exactly year, maybe in 2012 or so actually, so this question was asked. So you note down this, we are going to separate the real and imaginary parts. Note it down. Done? Okay. So here log z plus a. So this can be written as log of x plus a plus iy plus log x minus a plus iy minus log x plus iy. So this is the complex potential by separating the real and imaginary parts within the function. Now here this will be r e power I theta format if you write it. So r is equal to, for this one, x plus a whole square plus y square. So I call this as r1 e power I theta 1. And then for this r2 e power I theta 2. Theta is equal to tan inverse of y by x plus a. So r2 equal to x minus a whole square plus y square under root, and theta 2 is equal to tan inverse of y by x minus a. And then the third one is r3 e power I theta 3. R3 is equal to x square plus y square under root, and theta 3 equal to tan inverse of y by x. Now all these three together, log of r1 e power I theta 1 plus log of r2 e power I theta 2 plus log of r3 e power I theta 3. Now minus, yeah. Now this is log r1 plus log r2 minus log r3, and this will be the real part. And then I times of, so log e power I theta is nothing but theta 1 plus theta 2 minus theta 3. So this is by writing into the modulus and angle format or in the polar format. So the same thing I have written in the polar format, and then I have divided into real and imaginary parts. Now if I replace r1, r2, r3 in terms of x and y, then this is what is nothing but the scalar potential phi, and this is nothing but I times of tan inverse of y by x plus a plus tan inverse of y by x minus a minus tan inverse of y by x. So this part is nothing but psi for us, because w is equal to, this is the w. So w is nothing but phi plus I psi, where phi is this one and psi is this one. Got it? And this psi is essential component for us, because this will give the direction of the fluid flow for us. Got it? So you can note down this. Noted? Okay. So now actually we will further simplify the stream function psi. Psi is equal to tan inverse of y by x plus a plus tan inverse of y by x minus a minus tan inverse of y by x. Now we will add these two together. So this is tan inverse of y by x plus a plus y by x minus a divided by 1 minus y by x plus a into y by x minus a minus tan inverse of y by x. Now we have to simplify this. This is tan inverse of y into x minus a plus x plus a divided by x square minus a square minus y square. Yeah. Minus tan inverse of y by x. Got it? Yeah, I think this is correct. Yeah. So this is tan inverse of, so x plus x is 2x, 2xy divided by x square minus y square minus a square. So this is what is left over, minus tan inverse of y by x. Again, tan a minus b format you need to apply. So this is tan inverse of 2xy divided by x square minus y square minus a square minus y by x divided by 1 plus 2xy divided by x square minus y square minus a square into y by x. So this is the function which we need to simplify. So after simplifying this, what you are going to get it is tan inverse of y into x square plus y square plus a square divided by x into x square plus y square minus a square. So this is what we are going to get it, which is nothing but the psi. Got it? Now here, for streamlines, is nothing but psi is equal to constant. So if psi is equal to constant, then tan psi is nothing but, again it will be a constant k. So if you replace k is equal to y into x square plus y square plus a square divided by x into x square plus y square minus a square. Now this is what will give the stream function or streamlines. So for a constant value of c, so this is the streamlines equation, and the stream function psi is equal to constant will give the streamlines for us, right? So based on this diagram, we can identify how the fluid is flowing at any random location of x comma y, right? So this will give the fluid flow direction at any point for us. Now let us draw this case. Now here this is a, so there is one source here, and there is one sink here, and there is one sink here. Now from the sink, so sink actually will try to insert the water into the point, and the source will give the fluid outward, right? So the fluid is coming out from this, and the fluid is sinking here. Even here also, the fluid is coming out from here, and the sinking, so it is sinking at this particular point. Got it? Yeah. So that's correct. So this is the sink, and this is the source, and this is the sink. Now here actually whatever the fluid that comes, it has to go. So I think you might have drawn the magnetic field lines at early standard, right? Elementary standard actually you might have drawn the magnetic field lines. That's exactly what we are doing it here. So the fluid that is coming out of the source, it has to go and then sink at the sink. Now exactly on the other side also, it will be like this. Exactly from this side also, it will be like this. right? And then for different values of K, if you try to analyze it, it is different fluid line you are going to get it. Now here, not only from this side, the fluid that is coming out from here, or actually it has to sink from all the directions. So let us take, if K is equal to 0, then it will be y is equal to 0, right? If K is equal to 0, this part will be 0, and this can't be a real value. X square plus y square is equal to minus a square. So this is not a real value. Then y is equal to 0. It implies y is equal to 0, which is nothing but x line. So which is nothing but x axis. X axis is also a streamline for us. That means on the x axis, if you notice, this is the x axis. So this is how the fluid is coming. And even on the other side also, this is how the fluid is coming. Even here also, the fluid that got generated at this point, it will be traveling along the x axis and sinking at the other point. And it will be traveling on the negative x axis also, and it will be sinking at the other point where the sink is present here. Got it? So this is how the fluid is getting distributed. Now we'll take one more value of K. So let us say K is equal to infinite, which is nothing but 1 by 0, which essentially means that, so x into x square plus y square minus a square equal to 0. So if K is equal to infinite, then it implies x is equal to 0 is one solution, and x square plus y square is equal to a square is another solution. Now x is equal to 0 is nothing but y axis. So that is, this y axis will also form the streamline. So this is a source. So source actually will push the water out. So the fluid will go outward from the center along the y axis. So the fluid is going this way and going this way also. So this is the y axis line. And there is one more line, that is x square plus y square is equal to a square, which is nothing but the circle. So with the center at origin and the radius as a. So this is the circle. Now this radius is a. So this radius is a. Got it? So this is a complete system of the fluid flow. When there is a sink source present here, there is a sink present here, there is a sink present here. So for this, the complex potential, whatever we have analyzed is W is equal to log of Z minus A square by Z. So that complex potential will give this kind of fluid flow direction at any instant if you look at from the top. Got it? And then if you notice, as he said, the y-axis will divide the two of these things. So two of them, there are 3 points totally. Two sinks and one source. The source is present at the origin, and two sinks are getting subdivided by the y-axis into two parts, this part and this part. So the fluid flow lines also exactly subdivided with respect to the y-axis like this. And these are also circles and these are also circles. Got it? So this line actually is dividing one streamline exactly in the middle. So this circle streamline is getting divided. And from here, so these are not circles. This is the circle. Got it? Any questions on this? So, but totally, for us actually, you don't need to go deeper into the fluid dynamics in this case. What you need to do is, for us, it's only one thing. There is a complex function. That complex function, you have to bring in the format of the standard sources and sinks complex potential format. And then, once you bring it to that format, you identify the source and sinks presence there. And then, for the same complex potential, you divide the real and imaginary parts. We ignore the real part. Why? Because we are not very much interested in scalar potential. We always take up the stream function, that is psi. So that psi function is nothing but the imaginary part of the complex potential. You take it out, and then for that, for different values of psi is equal to constant, you are going to get different lines. Those lines will represent the direction of the fluid flow, which we call as the streamlines. Got it? So whatever may be the arrangement, this will be exactly the same procedure. Even if there is a presence of the circle, so that is, there is a source present, sorry, there is a cylinder present. Within that, if there is a source or if there is a sink, then you have to identify the system of images. So that images you have to identify and find out the complex potential of all the sources and sinks present, which will give rise to the method of image for that particular system. And then divide the real part and imaginary part. Take the imaginary part and draw the sketch of it. That's what is nothing but the stream function for us. So maybe a source, maybe a doublet, maybe a circle, maybe a rigid boundary or a boundary plane. Got it? But the procedure is exactly same, no difference at all. Clear? I hope no questions are there. But the simplification is not so easy. That is the complexity. That's why you need to practice it. Okay, so I will give you one problem as homework. So you try to solve on your own. I'll post the solution in Telegram. Note down this. In this case of the two-dimensional fluid motion produced by a source of strength M placed at a point S outside a rigid circular disc of radius A whose center is O. So that the velocity of slip of the fluid in contact with the disc is greatest. At the point where the line joining S to the ends of the diameter S to the ends of the diameter at right angles to OS cut the circle. And prove that its magnitude at these points is at these points is 2m into OS divided by OS square minus A square. So this is the problem statement what he has given. Now here, so here there is a cylinder like this, and there is a diameter here, and this is the point O, and this is the point S. Now this is a sink of strength minus m, and this is at point S, there is a source of magnitude plus m, and here there is a source of magnitude plus m. Got it? Now actually this is the arrangement he has given. So here minus m and plus m and plus m here. At any instant the complex potential will be, so for this actually plus m log z, and this is log z minus, so here actually this entire length, so the radius is a, I think, yeah. Yeah, so let us say this distance is c. If this is c, then this location will be, this radius is a, and this is a square by c. Yeah. Now here, this is a square by c from the origin. This is at a distance of c from the origin. This is at the origin. Here the complex potential will be W is equal to plus m log z minus m log z minus c minus m log z minus a square by c. So this is the complex potential. Yeah, that's correct. Got it? So this is the complex potential for all the sources and sinks at any random point, if you notice Z, right? So if you take Z here, the complex potential at this point is nothing but minus m log z minus a square by c minus m log z minus c plus m log z will be the complex potential at a randomly selected point. Now, if you know the complex potential W, the velocity is nothing but dW by dz. For this modulus is nothing but the velocity. Now, this velocity, you can find the maximum value of the velocity is by taking dq by dz, or actually dw by dz actually you can convert into the polar format. So there actually r or theta, whichever is convenient there. So there actually you need to take the derivative. In this case it will come as dq by d theta equate to 0, and then find the condition of this dq by d theta is equal to 0. Correspondingly substitute that condition in the velocity. You are going to get the velocity of the maximum point and minimum point. That point will be definitely these two locations. So here the velocity will be like this, which is perpendicular to the line joining OS. So this will be the direction, maybe this direction or maybe downward direction, but at this point you are going to get the maximum velocity point. So the procedure is just take the complex potential, find out the velocity, and then make sure the condition dq by d theta is equal to 0. That condition will give the maximum velocity value. That maximum velocity point you are going to get it at these 2 points. That's what he asked us to prove. Got it? But simplifying this is not so easy. And then finding out this dw by dz also, this is purely complex analysis, but a little bit complex. Understood? Okay, so you take this as homework and then try to solve it. Yeah. By evening, I am going to put the solution for this. So, any questions? Any questions? Yeah. Okay. Yeah. So, thank you. Yeah. Good morning. Bye bye.